Hello everyone. Once again welcome to our physics class. Hope you all are fine over there. Children, in the previous session we had completed our alternating current. Today we are going to discuss a new chapter, that is ray optics. And the fundamentals of ray optics had already discussed in class 10 physics. Okay, and some portions of this chapter has been deleted. So we will start with refraction of this chapter. Okay children, so let's get started with today's session. Children, let's start with the new chapter, chapter 9, ray optics. So let's begin with the basics of light. What do you mean by light? Light is a form of energy which enables us to see things around us. Whenever we enter into a dark room, we can't see anything. But the moment we switch on the light, we can see everything inside the room. So light is a form of energy which helps us to see everything around us. Now light travels in the straight path. That is the most basic concept related to light. It always travels in straight path. And speed of light in vacuum is a constant, and that constant value is denoted by c. The value is 3 into 10 raised to 8 meter per second. This is the speed of light in air or vacuum. Light waves are the most common form of electromagnetic waves. We will discuss more about electromagnetic waves in our chapter 8. Okay, so you just understand light wave is a form of electromagnetic wave. Then ray of light is the path of light wave traveling from one point to another. And you had studied about different types of ray diagrams in your class 10 physics, so you are familiar with a ray of light. So ray of light indicates the path of light. The arrow mark in that ray diagram shows the direction of light. Beam of light is a bunch of rays of light. So a group of rays can be considered as beam of light. Now what is refraction? You had already studied about refraction phenomena in detail in your class 10 physics. So light does not travel in the same direction in all media. You know, the velocity of light is different in different medium. In rarer medium, light travels with more velocity. In denser medium, light travels with less velocity. So with the difference in the medium, or with the difference in the density of the medium, the speed of light also varies. So when a light ray passes obliquely from rarer to denser medium, or vice versa, from denser to rarer medium also, there is a change in its direction of propagation. So let it be any medium. Whenever the light travels from one medium to another medium, there will be a change in its direction of propagation. That means the light ray will bend. Light ray cannot follow its same straight line path when it moves from one medium to another medium. This bending of light at the boundary between two media, when it passes from one medium to another, is termed as refraction. Okay, and it is more important, that is, it occurs only when the light ray passes obliquely from one medium to another medium. Whenever the light enters, or whenever the light is incident on a medium in a normal way, what happens? The bending of light ray is not observed. The light ray passes to the second medium without any deviation. And what is the cause of refraction? Refraction is due to change in speed of light as it enters from one transparent medium to another. So with the difference in density of the medium, the speed of light also changes, and due to that change in speed of light, refraction occurs. On the screen you can see one figure. It's very interesting. The spoon appears to be broken at the boundary, isn't it? This is air and this is that liquid. So at the boundary the spoon appears to be broken, but actually it is not broken. What is the cause of this image? This is due to refraction. Okay, and refraction phenomena is observed only when the light ray passes obliquely from one medium to another medium. Okay. Now what are the laws of refraction? See here, you can see one figure, and this is the boundary. This is the boundary, and this is the incident ray. The yellow portion represents the incident ray, and this small I is the angle of incidence. this is normal. So I is the angle between normal and the incident ray. And this medium has a refractive index N1. And when this ray passes from one medium to another medium, so the blue portion represents the another medium, second medium, and N2 is the refractive index of the second medium. So whenever light ray passes from one medium to another medium, this light ray will bend. Instead of following its same straight line path like this, the light ray will bend. That means refraction has occurred. So this is the refracted ray. This is the refracted ray, and this R represents the angle of refraction, angle between refracted ray and the normal. So what is the first law? First law of refraction states that the incident ray, refracted ray and the normal to the interface at the point of incidence all lie on the same plane. So here we can see the incident ray, refracted ray and the normal all lie on the same plane. And the second law of refraction. Second law of refraction states that the ratio of sine of angle of incidence, that means sin I, and to the sine of angle of refraction, that is sin R, is a constant. That is sin I by sin R equal to a constant, and that constant is nothing but n suffix 21, and this n21 is a constant which is known as refractive index of the second medium with respect to first medium. Okay, so n21 means refractive index of second medium with respect to first medium, and n12 means refractive index of first medium with respect to second medium. Okay, so this is Snell's law of refraction. Okay, Snell's law of refraction, and n21 is also written as n2 divided by n1. Similarly, n12 is also written as n1 divided by n2. And there is a relationship between refractive index and the velocity of light in different media. See, n2 by n1 can be equated to v1 by v2. Similarly, n1 by n2 can be equated to v2 by v1, where v1 is the speed of light in first medium and v2 is the speed of light in second medium. And if the first medium is air, then we can write the refractive index n21 is equal to c by v. Because the first medium is air, velocity of light or speed of light in air is denoted by c. So v1 is replaced by c. Then if there is no v1, then no sense in writing v2. So we can just write v here. And here also we can just consider n. So we will get a relation n is equal to c by v. And this is the absolute refractive index of a medium. So you had studied all these concepts in your class 10 physics. Now let's begin with the most important concept of this chapter, that is total internal reflection. Light travels from an optically denser medium to rarer medium. At the interface, it is partly reflected back into the same medium and partly refracted to the second medium. This reflection is called the internal reflection. If in total internal reflection phenomenon, there is no refraction and the entire incident ray will get reflected. So if we consider this as a boundary between two media, let this be our first medium, let this be our second medium. Now suppose first medium is a denser medium and second medium is a rarer medium. Okay, so a light ray incident at the denser medium, it is passing from denser to rarer medium. So at the point of incidence, we will construct a normal. Now, when it passes from denser to rarer medium, this light ray will bend, and light ray will bend away from the normal, isn't it? It will bend like this, away from the normal, because it is passing from denser to rarer medium. And what happens if light ray passes from rarer to denser? If light ray passes from rarer to denser medium, it will bend, and the bending occurs towards the normal like this. Okay, you have already studied about this concept in your class 10 physics. So whenever a light ray passes from denser to rarer medium, it will bend that the refracted ray will bend away from the normal. Now again, it is not necessary that the whole of the incident ray is refracted. From this, a small portion of the incident ray is also reflected back. So at the boundary, the incident light is partly reflected back into the same medium and partly refracted into the second medium. So this reflection is known as internal reflection because the incident ray is reflected back internally to the same medium. So that reflection is called internal reflection. But at a particular point, that means for a particular angle of incidence, a situation occurs where the whole of the incident light is reflected back. That means we can't observe this refraction phenomena. And this phenomenon is known as total internal reflection. And we can observe this total internal reflection only for a certain angle of incidence. So let's discuss about that. Now what is the condition for total internal reflection? So the first and foremost condition is that light ray should travel from denser to rarer medium. When a ray of light moves from a denser medium to a rarer medium, it moves away from the normal. That means the ray will get refracted at an angle R. We had already studied that. Whenever a light ray passes from denser to rarer medium, it will move away from the normal. Okay. Suppose we increase the angle of incidence. What happens? See, this is the normal. And suppose we have, this is angle of incidence initially. Now we have increased the angle of incidence. So when the angle of incidence is increased, correspondingly the angle of refraction also increases. Now this is the angle of refraction. Initially this was the angle of refraction. Now this is the angle of refraction. So when angle of incidence increases, angle of refraction also increases. So here it is written less, but it is not less, it is more actually. Sorry children for the mistake. So when we increase the angle of incidence, angle of refraction also increases. And a condition will come if we keep on increasing the angle of incidence, the angle of refraction becomes equal to 90 degree. That means again, if we increase the angle of incidence, what happens? Again, I increase the angle of incidence. A situation arises when the refracted ray will graze along this boundary like this. Now the refracted ray will graze along this boundary like this. So this is our refracted ray and this is normal. So this is the angle between refracted ray and normal. What is that? The angle of refraction, it is 90 degree. So for a particular angle of incidence, the angle of refraction becomes 90 degree. So this angle of incidence for which the angle of refraction becomes equal to 90 degree is known as critical angle. Critical angle, and it is denoted by I suffix C. So I suffix C is the critical angle. And what do you mean by critical angle? It is the angle of incidence for which the angle of refraction becomes equal to 90 degree. Okay. Now suppose again we increase the angle of incidence. Suppose the critical angle is 80 degree. Now again, if we increase the angle of incidence to 85 degree, we can't observe any refraction phenomena. For an angle of incidence greater than the critical angle, all of the incident ray is reflected back. So the incident ray is totally reflected back. This is total internal reflection. Okay. So what we had discussed is clearly represented in this figure. This is first medium, this is second medium. So this is the denser medium, this is the rarer medium. Light ray passes from denser to rarer medium. When the light ray is incident normally to the medium, it will move without any deviation like this. Now, suppose the ray is incident at this angle of incidence. So this is the angle of incidence. Then this is the angle of refraction. The refracted ray moves away from the normal. And secondly, the angle of incidence has been increased. So I dash is the angle of incidence now. So which is greater than I, the initial value. So when angle of incidence is increased, we can see the angle of refraction, that is R dash, also increases. Again the angle of incidence is increased. Now this is the angle of incidence, and when the angle of incidence is increased, we can see the refracted ray grazed along the surfaces like this. So what is the angle of refraction? This is the angle of refraction, 90 degree. So this is the angle of incidence for which the angle of refraction becomes equal to 90 degree, and this angle is known as critical angle. And again, if the angle of incidence is increased beyond this critical angle, no more refraction is observed. The whole of the incident ray is totally reflected back. Okay, so this is total internal reflection. So what are the two conditions for total internal reflection? First condition is that the light ray should travel from denser to rarer medium, and second condition is that angle of incidence should be greater than critical angle. So the total internal reflection phenomenon is observed only when the ray is incident at an angle greater than the critical angle. Okay. So these are the conditions to be satisfied for total internal reflection. And what do you mean by critical angle? See, critical angle is the angle of incidence where the angle of refraction becomes equal to 90 degree. Okay. What is the limiting factor beyond what the total internal reflection take place? Limiting factor is that the angle of incidence should be greater than angle of incidence for which the angle of refraction is 90 degree. That means angle of incidence should be greater than the critical angle. Okay. Now what are the applications of total internal reflection? The first application is that of optical fibers. Total internal reflection is used in optical fibers, and these optical fibers are used in telecommunication industries. Optical fibers work on the phenomenon of this total internal reflection. Okay, so these are some of the optical fibers for fancy decorative ideas, for telecommunication, and for all those purposes. For endoscopy in medical field also we will use this optical fiber. Now, characteristics of an optical fiber. They are small in size, light in weight. They have greater information carrying capacities than the metallic wires. What is the working of optical fibers? So this is the structure of optical fiber. Optical fibers are fabricated with high quality composite glass or quartz fibers. We can see our optical fibers are available in glass or quartz fibers, and each fiber consists of a core and cladding. See, core means the interior of that fiber is known as core, and on either side of the core a coating is done which is known as cladding. So cladding is observed at the ends or at the lateral sides of that optical fiber, and core is the interior portion of that fiber. The refractive index of the material of the core is higher than that of cladding. That is most important thing. The refractive index of core, that means the inner area, is greater than that of cladding. So which will be denser? There will be a difference in the density of the core and cladding. The refractive index of core is more, so its density will be more. The refractive index of cladding is less, so its density will be less. Okay, so there is a difference in density. So whenever a ray of light enters into the optical fiber, see, this is the point of entrance. So the ray enters from air to a medium. There will be a difference in density. So the light ray will bend, and this light ray will be incident on the cladding. This light ray is incident on the cladding in such a way that the angle of incidence is greater than the critical angle. this incident ray is made to fall on the cladding at an angle of incidence greater than the critical angle. We know whenever the angle of incidence exceeds the critical angle, it is totally reflected back. So this is the total internal reflection. This ray is totally reflected back, and this reflected ray is made to incident on this portion of the cladding at an angle of incidence greater than the critical angle. So what happens at this point also, the ray is totally reflected back, and at this point the reflected ray is allowed to fall at an angle greater than the critical angle. So at this point also total internal reflection takes place. So multiple total internal reflection takes place inside the optical fiber, and finally this light ray comes out of that optical fiber. So here, due to the difference in the densities of core and cladding, total internal reflection occurs. The conditions for the total internal reflection is also satisfied. That means the ray is passing from denser to rarer medium. So our core is a denser medium, cladding is a rarer medium. So the light ray passes from core to cladding, from denser to rarer medium. Here it is also from denser to rarer medium. Okay, so this is the working of optical fibers. So as there is a difference in the refractive index of core, and denser core acts as a denser medium and cladding acts as a rarer medium. So when a signal in the form of light is directed at one end of the fiber at a suitable angle, it undergoes repeated total internal reflections along the length of the fiber and finally comes out at the other end. Since light undergoes total internal reflection at each stage, there is no appreciable loss in the intensity of the light signal. So there is no much loss in the intensity of the light signal. Okay. So optical fibers are fabricated such that light reflected at one side of inner surface strikes the other at an angle larger than the critical angle. So every time the light is made to fall on the cladding at an angle greater than the critical angle. Even if the fiber is bent, light can easily travel along its length. Thus, an optical fiber can be used to act as an optical pipe. And there are glass and plastic optical fibers available in market. So, what are the comparison? We can just make a comparison between the both. So, the plastic optical fibers is cheaper. Glass is not so cheap. And the plastic one is flexible, but glass is not so flexible. Plastic one can withstand more stress, but glass cannot withstand much more stress. And the plastic optical fibers have less efficient transmission, but the glass optical fibers are more efficient in transmission over large distances. Okay, so these are some of the advantages and disadvantages of glass and plastic optical fibers. And what are the applications of optical fibers? See, total internal reflection is mainly used in optical fiber. And what are the applications of optical fibers? Where do we use optical fibers? So, first application is in medical field. It is used in endoscopy, fiber optic endoscopy. The first optical fiber transmit light from the body to the inside of the instrument. And second optical fiber will transmit from camera to the body. Okay, endoscopy is used to get the details about our internal organs. So for that purpose, this optical fiber is used. Then for decorative items, you can see a one lamp like thing on the screen. So different plastic strips, when electricity is passed, these strips will keep revolving, giving different colors. Okay. Then they are used in communication system, in the cables, and all for such communication systems we can use this optical fibers. Then it is also applied in prism and also in binoculars. So here you can see this is a binocular and this is eyepiece, and two prisms are arranged like this. In this position, two prisms are arranged. Okay, and what happens when light is incident here? What happens? Light enters through the lens and it enters into the prism and it undergoes total internal reflection and finally it comes out. Okay, so the prism makes use of total internal reflection by which it is useful in binoculars. Prisms designed to bend light by 90 degree or by 180 degree make use of the total internal reflection. Such a prism is also used to invert images without changing their size. In the first two cases, the critical angle for the material of the prism must be less than 45 degrees. So this is the principle in binoculars. See what happens. AB is the object and rays from the object are incident on the prism. And here the rays from A is incident on this face of the prism at an angle greater than the critical angle, so that the ray is totally reflected back. And here also the ray from B is made to incident on the prism at an angle greater than critical angle, so that the ray from B is also reflected back. And here also these two rays are made to fall on this face of the prism at an angle greater than the critical angle. So again these two rays are again reflected back, and finally these two rays emerge out from the prism and produce an inverted image of the object. Okay, and if we use multiple prisms, what happens? We can get an erect image. For example, if we use a second prism will again invert this inverted image and produce an erect image. Okay, so this principle is behind the binocular. So that's all about total internal reflection and its applications. With this I am concluding my session. We will meet in the next session. Till then, take care all of you. Notes and YouTube video based on the topic have been uploaded. Please go through it. Attend the test and post me the answers quickly. Stay home, stay safe all of you. Keep learning. Thank you.